What we're going to look at now is lactone hydrolysis, and if you remember what a lactone is, it's a cyclic ester, and what we're going to see is a situation where we have an OH and a C double bond OH in the same molecule as a product, and we've got an acidic and we've got a basic type mechanism as well. And what I want you to believe is that the mechanisms for the hydrolysis of lactones is going to be the same as the hydrolysis for esters. So let's go ahead and take a look at those mechanisms. So here is your lactone, and we're going to hydrolyze it. And look at the mechanism, it's going to follow the same steps. Alright, so the first step is the addition of H plus to the C double bond O. And that will put a positive charge on this C right here. And now we're going to have water come in with the O attacking the C plus. And now we're going to have this here with the positive charge on the oxygen. Now the next step is going to be crucial, because what we've got to do is figure out where the proton is going to be transferred to. And what we've always said is the proton will be transferred to the group that's leaving. Now the group that's leaving is actually the group that was originally attached to the C double bond O, which is going to be this group right here. So we know that the H plus will be transferred to this oxygen, which is this one right here. So I'm going to go ahead and do that. So even though it looks more complicated, it's still following the same pattern. Alright, so now we've got that. And now we can reform the C double bond O and kick out the leaving group. So it's really no different to what we've already done. And that would be the mechanism for the hydrolysis of a lactone. And again, I'm still trying to convince you here that it's following the same pattern as ester hydrolysis. Go back and take a look at the mini lecture for ester hydrolysis acid, and you'll see what I'm talking about. Alright, let's go take a look at the basic mechanism now. And again, it's going to follow pretty much the same pattern as we've already seen for the acyclic esters. So the OH negative is going to come in, attack the C double bond O. The electrons are going to jump up on the oxygen. Then we're going to have the negative come down and kick out the oxygen. Again, we're kicking out the leaving group. That's the Y group that I've been talking about, the leaving group. And then we can have the O negative come in and take this proton. Now remember, the reason this occurs is because we're forming a carboxylic acid in a basic solution. We have no choice but to have something remove that proton and form the carboxylate ion. The other way of looking at this is that this O negative is much more stable than this O negative. This O negative here is much more stable than this O negative because we've got a negative charge that is resonance stabilized, whereas this one is not resonance stabilized. And then we can have the H plus come in in a second step, and we can get our product. Okay, there's our product right there. Okay, the other way of doing this is at this step here, instead of the O negative coming in and taking this hydrogen, as we discussed with the acyclic esters, it's possible for the OH negative to take the H off the acid, and that'll give us water over here, and then we can have H plus added to both of those, and that will give us our product as well. So either way is okay, but we must somehow deprotonate that carboxylic acid when it forms in a basic solution. We just do not have a choice of doing this. Hang on, let me add a second H plus here. There we go, it's better. Right, so we'll have two H pluses being added, and that will give us our product.